Welcome to another podcast. In this episode, we're going to be taking a look at a method called the reduction of order method. And our reason for wanting to look at this is it's going to give us a way to find a second fundamental solution when we have a repeated real root. And so I want to go ahead and take a look at the method first by deriving it, and then we'll show how it can be used to find a second real root when we talk about the repeated real roots case. So I want to start with just sort of our standard form linear equation here, y double prime plus p of x y prime plus q of x y, and it's going to be homogeneous, so I'm going to set it equal to 0. Now what I want to do is I want to assume that y1 is a solution. So this is like saying that if we have a repeated real root, y1 equal e to the rx is the first root. Okay? Now, I want to suppose that if we have another solution, y2, it's some function times the first one. Now here v is a function of x, as are y1 and y2. V is called a variational parameter. We saw this earlier in the semester when we looked at the method of variation of parameters. And so what we're supposing here is that y2 can be written as another function of x times the solution that we already have. Now, if we plug this in, so if we plug this side into the original equation, what we're going to end up with then is v times y1 double prime plus p of x v y1 prime plus q of x v y1. So all I'm doing is plugging this solution in for y in the above equation. Okay, because both v and y1 are functions of x, then this is product rule. So if you trust me, I'll just go ahead and tell you what we get here. When you do product rule, you're going to wind up with this from the first piece plus p of x times, if you do the sort of our normal product rule now, you'll get v prime y1 plus v y1 prime plus q of x v times y1 equals 0. Now, I want to rearrange things slightly, and I think you'll see my reason for wanting to do that. I want to look at everything that involves a v. So if I look at everything that involves a v, I have v times y1 double prime plus p of x y1 prime plus, here we've got it again, we've got q of x y1. So those are all the terms that involve a v. We have one term that involves a v double prime, and the terms that involve the v prime are 2y1 prime plus p of x y1. Okay? Well, something happens here that's rather wonderful, and that is the original equation reappears in terms of y1. But we know that y1 is a solution. Since y1 is a solution, it has to satisfy this equation, which means this piece has to equal 0. Now if you look at what's left, I'm going to separate out variables here, get all the v's by themselves and all the y1s by themselves. And so I get v double prime over v prime equals -2. Let's see here, we get y1 prime over y1 minus p of x. And so all I've done is I've taken what was left over taking this right here, and I separated variables. Now, what happens if I integrate both sides of this? If I take the integral of this side and the integral of this side, then on the left-hand side, the integral of that side becomes the natural log of v prime. And that's equal to minus 2 natural log of y1 minus, and I've got an integral of this px term which I don't know, so I'll just have to leave the integral on it. Alright, if I take the exponential of both sides, I get v prime equals e to the negative 2 ln y1 times e to the negative integral p of x dx. Where have we seen that before? And so v prime is equal to, this term becomes 1 over the absolute value of y1 quantity squared times e to the integral p of x dx. Alright? Finally, I'm going to integrate one last time. So if I take the integral of both sides, this becomes v of x equals the integral of 1 over y1 squared e integral p of x dx. And I should have a dummy variable of integration here, which I'll just call dt. So this would mean that y1, well, actually I should have a dummy variable right here. So I just want to make sure that this comes out to be a function of x, right? Because the left-hand side is a function of x. So I need the right-hand side to be a function of x as well. So I'll make this a dummy variable t, and I'll make the outer integral x, so that it comes out to be a function of x. We have our formula. What this basically says is that if you're looking for a second solution, then that second solution, y2, is going to be equal to this v of x times the first solution. And so we're going to use this on this repeated roots case in an upcoming video. So I want you to make sure that you write this formula down, because we're about to use it in the next video, and I think it'll help you kind of understand what's going on in that next video. If you have it handy, you understand where it comes from, because we're about to turn right back around and use it. This is called the reduction of order method, and I want you to know what our assumptions were. The assumptions are the big thing here, okay? So the assumption was that y1 is a solution, and a second solution could be found by taking a variational parameter times the first solution. It's a very common technique in differential equations. And the main things that you need to carry away with you here are these two formulas at the end that are going to give us the second solution that we need for our fundamental set. All right, thank you for watching.